Okay. I think we're ready to get started. So today is a fantastic day because we're going to be talking about hypothesis testing. So have y'all covered that in any other classes? What kind of class was it?
I took forensic statistics last semester.
Okay. How hard did they hit that? Because I don't know anything about that course. So tell
We
us.
spent a lot of time on that. It was kind of like, I guess, the focus of the course. Kind of.
Yeah, well, that's the way it should be. Yeah, so this is like a mini version of that course. It's really just one lecture focused on, if you don't know what your null hypothesis is, you really have no business doing statistics, because that's what the statistical tests are helping you decide. And if you don't know the decision that you're trying to make when you're using statistics, then you're really working in the dark and you can't defend your decisions. So today is really essential on defending your decisions. So that's, and then we're going to use these tools, the different, let me see if I can use the laser pointer on this so it'll show up. Let's see if I can find it.
Okay.
Yes?
Did you post this slide on?
It should be. Is it not there?
I don't see it.
What are the ones that are for this week? What are they called?
Basic statistical figures, numeric and control training.
Okay, I'll have to check on it then. Let's see. No options. Let's see what this is. Yeah, here we go. Laser pointer. How about that? Yeah, look at that. All right, so we're going to talking about this. So this is the scenario for today, that we have a new employee. Okay, we're training a new employee. That's our trainee. We have a forensic chemist in our labs. And so we want to go to the vault and pull out a known sample, one that's been well characterized. And so the concentration of that sample is 13.2% by mass cocaine, plus or minus 0.1%. And so we have these two employees, and we want to see if they analyze the same sample, do they get the same answer, right? So that's the scenario. So we'll see if our training program worked well. And so in a perfect world, there'd be no statistically significant difference between the trainee and the forensic chemist, like for any employee. So if we go in and we give a particular sample of evidence or what have you to our employees, we don't want to have to keep track of the accurate person and the non-accurate person, right? We want everybody to be acceptable. Yes.
It's the right one. It just has like
a different title. Okay, good. That's good. I was thinking that was the case. So we'll see. And so how do we say that, how do we compare two different people? Well, we definitely compare them in accuracy and we compare them in precision. So those are the numerical ways to compare the people. There shouldn't be any difference in their results. There also, this is maybe a surprise to you, there shouldn't be any difference in the way they write reports either. So in this particular course, it is a writing component class, but it's not creative writing. Okay, your quality reports really shouldn't be different from each other. They have a different focus, a different topic, but the text should be very similar. The figures should be identical, really, just different data. And so in this particular case, when you're writing a standard report, that's not the time for you to get your creative juices flowing and try to come up with a different way to say it. You just say, this is the procedure, it was collected this way, it was analyzed that way, and you don't try to, make it sound narrative. It's not a novel, it's a report. And so in that case, this writing is very different. So, in terms of Turnitin, I should get a lot of similarity hits, because the way you describe your procedure ought to have a lot of the same words in it in the same order and everything. So that's dramatically different than any other kind of writing you've probably been asked to do, okay, where you're supposed to put it in your own words. In this case, you're really not putting things in your own words. You're trying to write a standard report. And whereas you may be collecting one type of data, that's different than someone else. But how you analyze it, like daily difference, yesterday was subtracted from today, that should be the same for everybody if you're doing daily difference. So here are the results. So just always look at the data to see if it makes sense. And that's what that silly acronym was. ANOG is this analysis of good. Is the data look good? Our true value was 13.2%. Here's the 20 data points, 10 for each. We kind of glance at it and we say, yeah, they all are around 13, right? There's some high 12s and some low 13s in both cases. You could also look to see the forensic chemists, they're all very low 13. So that's very nice, very tight grouping. You look at the trainee, I've got a 12.0 here, 11.5, a 15. So yeah, there's a lot more scatter in the trainee. So without even doing statistics, I could say something about the precision, couldn't I? Just looking at the data, I know that the forensic chemist is more precise than the trainee. Can you see that yourselves? Yeah. Okay. Now we'll see the numbers tell us the same thing, but if it's this dramatic a difference, right away you know where this is headed. Okay. Now in Minitab, you have some standard plots that you can do. This one is called an individual value plot. So each of these this is all of the data points for the trainee, and you can see the individual data points going all the way up. Here's that 15, down here is the 12, is 11.5. The true value is 13.2, that's the green line, plus or minus 0.1, those are the two yellow lines. So that's the accepted value, plus or minus the uncertainty. And you can see they both hit it, right? So the true value is contained in the spread of their data. And so you could say they're both accurate. They're not exactly the same, but they're pretty accurate. This is the mean here. So that's the mean of the trainee, which is coming in low. This is the mean of the forensic chemist, which is within the bars of uncertainty in terms of our accepted value. When these little dots are on the same line, that just means they have the same numerical value. So we have 4 of the forensic chemist values coming in at looks like 13.2, and then 3 of those coming in at 13.1. So like they nailed the exact value 4 times out of 10. So that's pretty good. So this is, again, a simple plot. You can just look at the data. You go to box plot or individual plot, and you select the 2 columns, and boom, that's what you get. Okay. Now I had to go in and enter this true value piece here, and so there was a little extra step for that. This is called a box plot or a box and whiskers plot. So they have the box here. This box goes from the 25th quartile to the 75th quartile. So 50% of the data is inside the box. And it has a line for the median, and it has a dot for the mean. So you can see the mean and the median are pretty close together. If those are close together, that means the data is fairly symmetric. It's not skewed one way or the other. Skewed data will move the mean. Okay, so the mean will be dragged out by an outlier. This up here is labeled as an outlier with a little asterisk. Otherwise, it would draw a whisker to that. The whiskers that come out of the box go to the minimum value and the maximum value, unless there's an outlier. And if there's an outlier, it goes to the next closest data point. So if they were to incorporate that outlier in calculating the mean, this mean would be a little higher. It would probably be right about there. Notice that this box contains the true value. Okay. So you could say, well, the uncertainty here does contain the true value. So, that's, you would say that's accurate. It still comes in low, though. The median and the mean both come in below the true value. Whereas up here for the forensic chemist, you see it's a much smaller box, much more precise person. You can see that the true value comes within that box on the box and whiskers plot. So we would say that they're both accurate because the boxes of uncertainty contain the true value. Later on, I'll show you a scale of what I use for accuracy, like is it excellent accuracy or poor accuracy or fair or good. And so I've got some criteria that are, I would just say that they're my operational definitions for describing accuracy as good or fair or poor. Okay. So we'll use those when we get to the numerical values. So here it is in Excel. Let's look at some of the figures of merit that we can calculate in Excel. A figure of merit is a number that captures the data set, right? So you're taking 10 values, and that's too many to talk about, right? We'd like to reduce that to one number. That one number is called a figure of merit. Okay. And so what's one of the numbers that we could calculate? The mean, right? We could take 10 data points and take the average. So that single value, that mean value, is describing all 10 data points. So that mean is a figure of merit. What are some others? Range. There's another one, and standard deviation. So those are three different ways, three different figures of merit that we could use to describe 10 data points, 1,000 data points, and so on. Okay. So here's our true value. Here's our 10 data points. So here's the mean at 12.9 for the trainee, 13.3 for the forensic chemist, and this is the Excel formula, the average, and it's showing the cell references for column C. But if for the trainee, you would just use the cell references for column B. So you've used Excel quite a bit. That shouldn't be a problem for you. The range, again, you can use this max function. Instead of digging through the data, trying to find the maximum value and the minimum value, just use these functions in Excel. So this takes the maximum value for that data set and subtracts the minimum value for that data set. So Excel can search and find the max and the min. So I put all these formulas in here because one of the exercises, the homework exercises, is to go through and repeat all of these calculations in Excel using these formulas so that you've done it yourself once. And then you'll have all of these, and they get a little bit more complicated than these. These are the easy ones. These are the ones you probably could figure out on your own, but there's some others that are not so straightforward. Then we get to the standard deviation. Now there's two different types of standard deviation. There's the sample and the population. Let's go over here. The pen. And so this right here in Excel, they have this .s. So that's for a sample. And so if you did stdev.p would be for population. And if you had 15 or more data points, then you would use the .p instead of the .s. The .s will be slightly larger than the .p. So you can look at this now and you could say that the mean value or average value plus or minus s, does it contain the true value for the trainee? And so here we have the mean, 12.9. Here's the standard deviation, 0.9. So 12.9, if you add 0.9 to that, it gets up to 13.8. And so yes, because it goes up to 13.8, that contains 13.2. And so we would say that the uncertainty, even plus or minus 1 sigma, contains the accepted value. We couldn't do this for the last data set that we analyzed because we didn't know the true value. You know, we were doing the precision calculations last time, but we didn't have a true value. So we couldn't calculate the accuracy. We could only calculate the precision. But for this particular experiment, we know that, or at least the accepted value for that cocaine sample is 13.2. So now we can test the accuracy. So we would say that the trainee in this particular situation is accurate. Okay. What about the forensic chemist? Okay, so 13.3 plus or minus 0.2. So here's our standard deviation, 0.2. When you have a really small standard deviation like this, it allows you to be confident if you have bias or not. So if something comes out as inaccurate, like the true value is not within your bounds, then you've detected your bias. You've detected that you've got a systematic error. Everything is high or everything is low. It's very precisely determined, but somewhere there's a bias knocking you off. Even if it's a 0.1%, you have a bias, and then you need to explore what might be biasing your data high or low. Okay. In this case, it does contain, that 0.2 gets us up to 13.5, and so and down to 13.1. And so it's 13.3, which comes in a little bit high, but that 0.2 is enough to capture our true value of 13.2. So we would say that the forensic chemist is accurate as well. Okay. Any questions on this page? Okay, so these are our conclusions. Numerically, both seem to be accurate because their means and standard deviations contain the accepted value. Okay, so now we get into some of the hypothesis testing parts. And so here's the null hypotheses for today's lecture examples. So we're going to test that data point for an outlier. And our null hypothesis would be the data point is not an outlier. We're going to test to see if the trainee and the forensic chemist are from the same population of data. What does that mean? Can you explain to me why like how that null hypothesis is connected to what we're doing in the lab? What does it mean that they're from the same population? It says they have the same mean, but what is, put that in your own words. Like, I'm going to wait you out on this because I want y'all to think about it.
Theoretically, if the point's not an outlier, you remove it, then the mean will change that much.
Okay. This is, so we're testing, these null hypotheses are not related to each other. Okay, so that's all right. That's and so we're doing three major tests. The outlier test is whether that high point, that 15, is an outlier. So that'll be its own independent discussion. Then the second test that we'll do will be this next one, to see if the trainee and the forensic chemist are from the same population. That's statistics speak. So how does that relate to the lab? What are we saying if they are from the same population, and what are we saying if they aren't from the same population? Yes?
I'm guessing that if they're not from the same population, then the true values would be different.
It would appear that they are. Yeah, it would appear that we know they aren't the same because they came from the same set of samples. But if we didn't know that, we would look at the trainee data and the forensic chemist data, and like you're saying, are they testing the same sample? It would appear that they're not. If they're dramatically different, then we would say they're not from the same population, meaning my trainee is so different than my forensic chemist, I can't be confident that they're testing the same thing. That's really bad, isn't it? You know, so I know they're testing the same thing because I set this trial up. But once I lose that, if they're both testing unknowns, then I will have a different answer completely if I use the trainee versus the forensic chemist. If they don't appear to be from the same population in this particular case. I know they're from the same population. I have this lab sample that they both tested. And so my null hypothesis is that they're from the same population. If the results come out dramatically different, then this hypothesis fails.
Is that more helpful in round robin?
Yeah, so this would be the null hypothesis if we set up a round robin and we sent this around to 3 labs or 4 labs. The null hypothesis would be that every lab is from the same population. We know that to be the case because we set it up. But then we would look at their results to see if their results statistically match that null hypothesis, right? And so we're kind of doing a round robin with 2 different people. We know the samples true value and uncertainty, and then we're having them both test it and see. So ideally, we would hide that result from them. We say, here's the samples, test them, tell me what you've got, and then we would know the true value, they would not. So that they don't look at that outlier 15 and then kind of turn the knob to make sure some more numbers come out low so that they could get their mean back down to where they think the true value is. That's the problem when you're doing titrations. Remember that freshman chemistry, you do a titration and you get a color change, then you're coming along and you're like, oh, I want to make sure that, I slow down in this region, and you want your numbers to be really close to each other. And so instead of going until it's exactly the same color that you want, you're like, yeah, that's good enough because you're biasing it low or biasing it high. So a lot of times we will just, it's almost subconscious that you, you put your thumb on the scale, so metaphorically to make it weigh what you want it to weigh. Okay, and that's a real problem. You really should try to isolate your desires from your results. It's a lot easier with instrumental analysis because you put it in the instrument and you get the numbers that you get. You can't really tweak it, to make it bend to your will. So this is the second null hypothesis we're going to use, that the trainee and the forensic data sets are from the same population. What is the third one? The trainee and the forensic chemist data sets have the same variance. Now, we looked at that. We know that's not the case. I mean, we could tell from the data that the trainee is really spread out and the forensic chemist is really tight in terms of the data. But we'll do the statistical test to show how we test that numerically. Now, variance is the standard deviation squared, and so that's just your uncertainty squared. So let's talk about our decisions that we make on these null hypotheses. If the probability, so this is using the statistical terms, this p-value, so the probability that the null hypothesis is true is less than 0.05, then reject the null hypothesis. And so that's a pretty stringent test if you think about it. If there's just a 6% chance that the null hypothesis is true, we'll accept it. That's pretty weird, isn't it? There's only a 6% chance that the trainee and the forensic chemist data have the same mean. We're going to say good enough, 6% chance. Okay, and we part of the reason we're comfortable with that is because we're only testing it 10 times. And so it depends upon the variability of our sampling and so on. And so we're saying, all right, if it's even 6% chance that they're from the same mean or the same package, the same population, then we'll say yes, that we fail to reject that null hypothesis. But if it's a 5% chance or less, then we'll reject it. So if the probability is less than 5% that the null hypothesis is true, then we reject it. This 0.05 is called alpha. So that's definitely a term you want to put in your brain. So when we talk about the alpha value for a statistical test, this is what we're talking about here.
Does that ever change?
For 95% confidence, it's always 0.05. And so 1 minus alpha is our confidence. So when you see alpha of 0.05, you know you're operating at 95%. So naturally, what would be the alpha for 99%?
0.01.
0.01, yeah, yes, exactly. And then if you can't state your null hypothesis clearly and concisely, you have no business doing statistics, because this is what you're testing with your statistical test. You're going to get p-values. So when you get these p-values right here, you got those all in PChem, and you compare them to 0.05, and a lot of them are really low. And so you're like, great, I got a good p-value, so I can trust this M or B value in my linear regression. But you probably couldn't have stated the null hypothesis in all of those analyses in PChem because you were just learning how to do it. But the null hypothesis in all of those cases was that the coefficients for each of the columns was just there because of random noise. So random noise in the data created all of those coefficients. So when you got a p-value for, say, the vibrational frequency in the carbon monoxide lab, and the p-value was something like 10 to the minus 8 or 10 to the minus 15, that was the probability that random scatter in the data from your peak picking gave you that vibrational frequency. It's a really low probability. And so that's why your p-values were so low, because you got really good coefficients. You peak picked, 1 million points. Remember how tedious it was. And all of that peak picking led you to a good linear regression, and you had really low p-values. And that's what we get from a lot of those PChem analyses. Now let's look at the outlier test. There's 2 outlier tests that we teach. This one is I've only seen this one in analytical chemistry. I haven't really heard anybody else talk about Dixons Q test, but I'll teach it to you because it, again, is used in a lot of analytical labs. The table that I found for this value was from this Fundamentals of Analytical Chemistry, and then they cite this paper in Analytical Chemistry from 1991. So these were the critical values of Q, and this is how we use it. So what we're doing is we're taking this gap over this range. So this is the value for Q experimental up here, these equations. And so when I talk about gap and range, we have a questioned data point here. So this is the number that we're questioning. We're trying to see, is that number an outlier? It's going to either be the high number or the low number, right? Just think about it. You've got 10 numbers. You're not worried about any of the ones in the middle of that range being an outlier. It's always either the highest one or the lowest one, the one that stands out from the pack. Now, if you know you spilled your sample, you throw that data point out. This is for the data points that you have no reason in your notebook or in your experience to question. You did it just the same as every other one. Now, maybe there really was something different about that sample. Maybe you did a pipette and there was an air bubble in the tip, and you didn't notice the air bubble. And so when you thought you delivered 300 microliters, it was really 200 microliters, and it was way off. You just didn't catch that air bubble. Okay, so there's a lot of reasons that went unnoticed why you might have an outlier. And this is what you would use to question those data points. So if there's no known reasons for an outlier data point, you can use this. So we take this gap over here. So we take that number and subtract the nearest number to it. So if it's the maximum, we take the maximum and we find the gap to the nearest number next to it. If it's the minimum, the same thing. The minimum number minus the one next to it. And we don't want that to be negative. And so we take the absolute value, right? We're just trying to get the gap over the range. And so we're taking how much of the range is captured by that gap is the question.
Do we use the outlier maximum?
Yes. Yes. Good question. So let me draw a little number line here. So we've got a number line here, and we've got, say, two data points here and one way over here. Okay. So the range is here, right? The full range, including that data point. So that's this range. And then this is the gap. And you can see that the gap takes up most of the range. So that's going to be a value pretty close to 1, right? Because it's very close to the full range. And you can see that these critical values, they get really close to 1 when you have 3 data points like this. So it's trying to say this, the gap, 99.4% of the range. So you have 2 really close data points and then a huge gap. And so that's the test. So how do we use the test then? So we calculate this experimental Q value, and the null hypothesis is that question point is not an outlier. Okay. And so if the Q experimental is greater than the Q critical, then we reject the null hypothesis. Okay. So again, we start from the standpoint that all the data is good. If we do this and Q experimental is greater than Q critical, then we reject that null hypothesis. And it gets easier and easier to reject the more data points we have, because you're going to get a better feel for the trend of the data if you have 10 data points versus 3. Okay. And so in this case, we have 10 data points with our forensic chemist and for our trainee. And so this is going to be our Q critical at 95% confidence. So you come over here, you can see Q95, that's the alpha of 0.05. So wherever these, you find it in the table. Okay. Pretty straightforward. Now we'll do that test in Excel in a little bit. So that's the Q test. Let's look at the Z transform, the Grubs test or the Z transform. This one's based upon a normal distribution curve. So look at this. That should look familiar. That's the same value for the 95% confidence. What this is saying how much of a chance would there be for my data point to be 1.96 away from the mean, well, there'd be a 95% chance that it's within that value. So this is our critical value for this normality test or Grubbs test. So again, this is for if there's no known reason for producing an outlier. It's based on a Gaussian distribution that has a mean of 0 and a standard deviation of 1. And then you can compare your z-value to the cutoff z-values. And our null hypothesis is the same, that the question data point is not an outlier if your questioned z-value is greater than z-critical, then reject that. So here's how we calculate the Grubbs or the z-transform. Notice we take now, instead of subtracting the nearest neighbor, we're subtracting the mean. So we're seeing how far away from the mean is our questioned data point. And then we're dividing that by the standard deviation. So we just calculate the mean, the standard deviation. We look at our question data point and say, look how far away from the mean it is. What's the probability that a normal distribution would give a data point that far away? Okay. And if it doesn't fall within the 95% range, then there's less than a 2.5% chance on either side, less than a 2.5% chance that that data point is inside this population, so we can throw it out. So we'll do this one in Excel as well. So here's our nearest neighbor and our maximum. So I've rearranged the data so that they were on the same row, so it would be easy to see. Okay, so it's not a coincidence. I actually moved the data points around. So this is our maximum value for the forensic chemist. This is our maximum value for the trainee. Here's our nearest neighbors. And so for the Q test, I take 15 minus 13.3 and then divide that by the range. And so here's our Q test. It's 0.46. So that was the 15 minus the 13.3 divided by the range for the trainee. So 0.486. This was the critical value from the Q test for 10 data points, which is 0.466. And so my question Q or experimental Q is greater than the critical Q, and so this is rejected as an outlier. And in our box plot, this is a clue, right? And it was up here as a little asterisk. So it told us, but still, this is how we do the numbers. Okay. Let's look at the Z transform. So if we take our maximum, this 15, and subtract it from the mean, okay, and divide by the standard deviation, this is what we get. We get 2.3. Okay, so that's our what's called a Z transform. That's our Z experimental. This is the Z critical, so it's greater than Z critical. So it's also an outlier using the Grubbs test. We could also test our maximum value for the forensic chemist. So 13.7 minus 13.5 divided by the range gives us 0.33. And that's less than the Q critical. We could take the 13.7, subtract the mean, and divide by the standard deviation, and we get 2.15. And so that's kind of interesting. It's showing up as an outlier because our forensic chemist is so tight. Okay. So we've got kind of a weird situation. It says for the forensic chemist, it says an outlier based on the Grubbs test, not an outlier based on the Dixons Q test. What would you do in that situation? Which is the more conservative decision? So we have two choices. We could throw it out. What would be the ramifications of throwing it out? Reduce the total number of samples, for sure.
You can also possibly make the trainees data look better, even if their technique is not as good.
Okay, so that's interesting. Let's put the trainee aside and focus just on the forensic chemist. If we throw out the outlier, what will we do to the range? Shorten it. What will we do to the standard deviation? Shorten it. Yeah, reduce it. And so anything that increases our uncertainty, we would call that a conservative estimate, right? We don't want to overstate. So I would say keeping it in is a more conservative it's our null hypothesis, right? Our null hypothesis is it's not an outlier. We have kind of mixed results. Under one test, it's an outlier. The other test, it's not. It's probably safer or more conservative to keep it, because again, that keeps our uncertainty as high. We're more confident if we have a higher uncertainty. That sounds backwards, doesn't it? Okay, but again, we're let's say we don't know the true value, and so if I have a wider uncertainty, I'm more confident that I'm going to get the true value inside my uncertainty. And so that's going to be the more conservative estimate, is to keep it. Whereas the trainee comes in as an outlier on both. Okay, so we can take that one out. That will reduce our uncertainty. It will reduce our range, but it's definitely an outlier on both of those. It's quite a bit larger than the critical values. So this is a good example where we kind of have to choose, if we get these mixed results, it's best to go with keeping the data point. Okay, so let's look at the accuracy. So that was we've reduced the data by one data point for the trainee. And so notice I have a trainee column here that has the mean and the standard deviation and everything. And now I've got a trainee without the outlier. So I'm going to have another column now and redo a lot of those numbers to take that outlier out of the trainee data. Okay, so here's our error values. So let's calculate the error values. Here's our median or middle value. Here's the standard absolute error. So look at the absolute error, and that's calculated over here. So that's the mean minus the true value. The order matters. Okay. Why do I say the order matters? Why do I want to subtract the true value? Especially for the absolute and percent errors. What if the mean is low? So if I calculate the mean and it's less than the true value, what will the error result be? Negative. Does that tell you something? Like when you see a negative sign, if I say my error is negative 0.33, that tells me the trainee is low because it's negative. If you swap this value, you'll reverse the sign. And that would be misleading. If I would say that my error in my trainee is plus 0.3, it sounds like I'm high. And so if you reverse that order, you're gonna reverse the natural tendency to think that positive numbers are above something and negative numbers are below something, right? So when I'm reporting error, I want to make sure that I subtract the literature value or I subtract the true value, so that if my mean is below the literature, it comes out negative. If my mean is below the true value, it comes out negative. Okay, so the sign matters because that communicates something. And so this is telling me that the trainee is low by 0.33%. It's low by 0.33%. So that's mass percent. Now I could calculate the percent error. So I have the absolute error divided by the true value times 100%. Okay, and so then it says I'm low by 2.5%. So negative 2.5% is my percent error. And then this right here says, are they accurate? I would say that that's fair accuracy. Now, where do I get that number? I say fairly accurate. Well, this is DW's criterion. Okay. And just my experience in reading reports and so on, that it seems to be a good rule of thumb to use these cutoffs. If you're within 1% of the true value, that's excellent. If you're biased off by like 0.9%, that's great. That's excellent accuracy. Between 1 to 2, that would be good. So this one is between 2 and 5. So it's fairly accurate. It's within 5%. Okay. It's not as good as 2%, not as good as 1%, but it's within 5%. So I would call that fair. If it's off by more than 5%, I would say that's poorly. It's poor accuracy. Okay. You missed the value by 5% or more. So I'm going to call that fair. let's look at it now with the precision. So we have our standard deviation, 0.88, and we can do the relative standard deviation, so that S divided by the mean value. So that's 0.072. Again, that's going to be in whatever units we're measuring. So these are in percent cocaine by mass. So that's my uncertainty in percent cocaine by mass. If I take that times 100%, then I end up just in terms of a unitless value, percent uncertainty or coefficient of variation of 7.2%. Now I could use this same scale for my CV. See up here, the CV or percent error, and I'm at 7% error. And that's poor, right? It's more than 5%. And so for my precision on my trainee containing the outlier, I would say that's poor precision. And so you can see that down here. Okay, our confidence intervals. So here's our, let's see, here's my standard deviation. If I take that and multiply that by 1.96, then here's my confidence interval. It goes down to 12.2 and plus up to 13.5. And so is this person precise? I would say with a 7.2% CV, that no, it's not very precise. It's poor precision. This contains my true value, so it's fair. Am I coming in biased low? But it's fair accuracy. Let's now look at the trainee. So we took out that high value of 15, recalculated all of these numbers. What it did was when we took out that top value, it biased it even more low. So taking out that top value reduced our mean. Let's see, where's the mean? Yeah, it dropped it down. Let's see. The mean went from 12.9 to 12.6. It actually got further away from the true value. So now our percent error comes in at negative 4.3%, which is fair. It's still within 5%, but it did get worse. Then we can look at the precision. The precision should have improved, and it did. It went from 7.2% uncertainty to 4.6%. And so that went from poor to fair after we got rid of that outlier. So, our trainee's not bad. They've been trained. Okay. They're just not up to the same level of performance as the forensic chemist. So here's the forensic chemist stuff. We kept that 13.7. Here's our accuracy. So our mean was 13.3. Our true value was 13.2. So our absolute error was 0.07. Our coefficient of variation was 0.5. So less than 1% off. So that's fantastic. So we call that excellent accuracy. That's what we would expect from our seasoned professional. And here we have our standard deviation, which gives us this coefficient of variation of 1.5%. Our confidence interval was 0.14. That's going to contain our true value, and our precision is good. So we're not within 1%, but we are inside of 2%, so I would call that good precision versus fair. Does that make sense? Okay, so these are the numbers in Excel. Here's all of the formulas for calculating these figures of merit. All right, so these are just judgment calls, these fair and poor and good judgment calls or excellent, using that little table that I have up there. Let's look numerically to see if they are giving the same mean value and the same standard deviation or the same variance. So to report a standard deviation for the whole lab, we need to use that pooled standard deviation. So this is the pooled standard deviation equation, and this pooled standard deviation is also needed for the t-test for equal means. So you should get good with calculating that pooled standard deviation. And here's the t-test for equal means. And remember, after we pull that outlier out, these are not the same values. So like one of these would be 9, the other would be 10. So you go in and get the data points, the number of data points for each of those. what it's doing is it's testing the difference in the means divided by the pooled standard deviation and scaling that by the number of data points that you have. So here's the null hypothesis for our t-test for equal means. So this is seeing if their means are different enough that it appears that they got these samples from different drawers. Right? We know they didn't, but this is testing, is this person giving exactly the same mean as the other one, or statistically a similar mean. So we calculate t experimental using this equation, and then since our trainee could be high or low, we have a two-tailed t-test. And so this breaks some people's brains, but when we have an alpha of 0.5 and we have two tails, what does that mean, two tails? Let's go over here and look at it. So here's our true value. Okay, and we've got some distribution. When we calculate the 5% confidence interval, it's getting 0.95% of that area. So over here is 0.025, and over here is 0.025. Those add up to our alpha. So for the t-test, we're trying to see if it's unreasonably high or unreasonably low. So we're going to use half of our alpha to test for each one of those. And so this is the formula in Excel. And so this would be our half of our alpha. So right here. And where did the 8 come from? That came from the degrees of freedom. For our smallest data set. So that would be n minus 1, and this was 9 minus 1 equals 8. Okay, so we use that smaller data set for the trainee as the degrees of freedom. And so that's going to give us our critical t value. We can get that from Excel using this. You can also look them up in tables, but it's nice just to use, since we're using Excel anyway, just to use this function that will give us our critical t value. So if the experimental t that was calculated with this equation up here is greater than our critical t, then we would reject our null hypothesis. And here's some of the, like an example of the table that you get. So you have data points here, all the way up to 10. We have these critical t values at 0.975. So that's, again, one side of that distribution. So here's our results. So we have the pooled standard deviation. Let's see, right here, 0.32. That's with keeping the outlier. So I just did it still all the way down. I did all of these tests with the outlier and without the outlier. After we killed the outlier, we should not do all of those calculations. We should only use that middle column of without the outlier. But just for grins, I did it containing the outlier and then not containing the outlier. Okay. So this is that that pooled standard deviation. Here's the t-test for all of the data. So this is our experimental t-test. Okay. And then here's our t-inverse function. Okay. 2.69. It's using 9 here because we kept that outlier for this one. Okay. Yeah. And so for this column, we would have an 8. And that's why those numbers are different. So our t is greater than the t-table or t-critical. Therefore, the means are not the same. So that's dramatic. It's saying that they have a different enough answer that they're not getting the same answer. Right? They analyze the same sample from the same population, but statistically, it looks like it's 2 different populations. It's 2 different seizures. So, and then we threw the outlier out. We get a much larger t experimental, And the reason that is because our uncertainties narrowed down. And so this even makes it worse because they're saying, wow, now the trainee has a better certainty for their answer and their means are different. So this really dramatically says that their means are different. Notice we only have, we have 3 columns of data, but we compared this column to that column and this column to that column. So we're only going to have 2 results. If we threw this column out, let's see, we would only have 1 comparison. So if we threw this one out, then we would just have the trainee without the outlier and the forensic chemist. And so whenever you're doing the t-test for equal means, you're just comparing this person to that person. You only have 1 comparison. So we wouldn't have anything to put under this column here. Let's do the t-test for equal variances. And so this is testing to see if their precisions are the same. So the null hypothesis is that the trainee and the forensic chemist data have the same variance or the same standard deviations. So we calculate F experimental. This one's a lot easier to calculate than the t-test. We don't need a pooled standard deviation. We don't need, a whole lot of mess with the degrees of freedom or anything like that. We just calculate this F experimental value, and that is the ratio of the variances. So we have the standard deviation squared for person 1 divided by the standard deviation squared for person 2. Since our trainee could be high or low, we have a 2-tailed F test. And once again, we use the alpha of 0.25 for the low side and 0.975 for the high side. So we have to calculate 2 F critical values, F upper and an F lower. So this is the F upper value. And we have the degrees of freedom for each. This was for n equals 9, so 9 minus 1 is 8. This was for the forensic chemist, n equals 10, so 10 minus 1 is 9. And this is the 0.025, so this is our 4.1 is our critical value. And then the lower one, I don't exactly know why this one comes out a lot higher because it's a 0.025, but this one comes out lower because it's 0.975, but that's how the numbers work out. This would be our F lower because it's the lower one, the smaller number of 0.23. So how do we do this test? We have 2 critical values. So this is our criterion. Look where the F experimental is. We're saying if it's between these. So if it is greater than the lower value and less than the upper value, fine. Right? It's within that range. Then we would not reject the null hypothesis. But if it's outside either one of those, if it jumps out of the acceptable range of F, then we would throw it out. Or we would reject the null hypothesis, which means that the null hypothesis is that they have the same variance. We would reject that if it hops out of this acceptable range of the F value. So let's look at our numbers in Excel. So here's our upper F value. Let's see, on my pen. Here's the F upper. If we kept the outlier, here's the F lower. Let's see. Where's the lower one? Oh no, this is the experimental. This is F experimental. So F EXP. And then this is the lower F value, and this is the upper F value. So you see 21 is much, much greater than 4. So it's outside that range. So F is greater than F upper, so the variances are not the same. We reject the null hypothesis. Let's take that outlier away. This will improve our standard deviation for the trainee. It gives us a smaller F experimental. We have a slightly different range because we have different numbers of data points for the trainee, but this is still greater than the upper, and so the variances are not the same. So even after taking out that outlier, they definitely have different precision. So these are the statistical ways to capture what you saw at the very beginning. We looked at that data. The trainees' data was all over the place. It went from 11 to 15, lots of 12s, a few 13s. It did kind of capture the true value, but the scatter was all over the place. You looked at the forensic chemist. The data was really tight. Four of those values were right on the true value or accepted value. So we knew that the trainee was much more precise. But just looking at the data and giving your professional opinion, it's valuable. We can look at the data and say, hey, that's what that says. But this is a more defensible way. You can now say that, at a 95% confidence, they definitely have different precision. 95% confidence, they definitely have different means. They're giving different answers. So we just need to train the trainee a little bit more. Let's have them shadow the forensic chemist and look at their technique for pipetting. Look at all of the different things that they do. What are the ways they inject the samples, or any of the little nuances that is different between them need to be fixed so that they give the same results. So these are the ones we used so far, that the trainee and the forensic data sets. This is the null hypothesis. This was rejected by the t-test. So our null hypothesis was rejected because there were statistically significant differences between their means. The null hypothesis that they have the same variance was also rejected because the F-test showed us that they had statistically significantly different variances. Now we can do some of this stuff really quickly in Minitab. This right up here is you can go up to the menu statistics, basic statistics, and over here you have the two sample t-test, and then it shows you your columns of data over here. You have a sample number column, you have trainee data, and forensic chemist data. And you come in here, the samples in different columns. The first set of samples is the trainee, the second sample. So you just click your cursor in here and then click the column, and it'll put it in there automatically. And then you come down and you can hit this little graphs button, and you can get an individual data plot or a box plot and hit OK and hit OK, and it does all that for you. When you did the box plot, you got the ruling that was an outlier. And so I think if you dig it through there, I think it's using the, I'm pretty sure it's using the Grubs test, the Z value, not the Q. Because again, the Q I've only seen it used in analytical chemistry, and Minitab is just a generic statistics package. So, but you would dig through the help here and see, all the details related to every one of these options. It's got a really good help. In fact, there's a stats textbook as a part of the help file in Minitab that can teach you a lot of these things. You can go in there and find a lot of information. Do they have the same variance? You can come up here and go to stats, basic statistics. Down here, you have, again, two variances. Click that, you get this plot. And this is kind of a really weird one. It tells you the uncertainty for the forensic chemist. It tells you the uncertainty, so the standard deviation for the trainee. And then, this breaks my brain, it gives you a confidence interval on their standard deviation. That's weird, isn't it? Normally we report the mean with a confidence interval. Okay, this is reporting the standard deviation with a confidence interval on the standard deviation. I don't know how they calculate that. I need to go to the help file and figure out how do they get a plus minus on the standard deviation. I have no idea how they calculate that. But one thing I do know is that the confidence intervals don't overlap. Like, this is the estimate of the low end of the confidence interval for the uncertainty for the trainee, and this is the higher end for the uncertainty estimate on the forensic chemist, and they don't overlap. Anytime you have confidence intervals that don't overlap, you know just from that picture that they're significantly different. Okay, and so this is saying that the uncertainty for the trainee and the uncertainty for the forensic chemists are different. You could also look at the p-value. The p-value is testing the probability that there's no difference, and up here it shows 0. Okay. Now you'd have to kind of assume that it's rounded to 4 decimal places or 3 decimal places, and so you can't really say that the p-value is 0, but it would round up to 1 right here if it were greater than 0.0005, right? And so it didn't round up, so we know it's less than 0.0005. So you could say that there's a less than a 0.0005 chance that these are the same. Okay. Now, why did we decide on 10 samples for each? So this is a question that no one asked, but it's probably one of the most important questions to ask. If we're going to compare these two persons, or we're going to compare these two drug seizures, or we've got, in this seizure out of this trunk, we've got 50 blue baggies and 50 green baggies. Are they the same? How many do we sample from those 50 or 100? Right? How do we decide on the number of runs? That's a huge question. And this is what we would use, this guide to uncertainty management. Now, it gets really detailed, and you can come up here and you can decide, well, if I've got a known uncertainty in terms of my acceptable error rate, and I've got the expected uncertainty in the sample, not the instrument, then I can figure out how many lab samples to run. But these numbers are really hard to get. You're only going to have those with years and years of experience in terms of what your lab is processing. So these guidances are great for crime labs that have a long pedigree with their instruments and their samples that they get and so on. So I don't really know how, if it's an unknown situation, how you would use these equations. And so I end up using this rule of thumb. So if you have less than 20 samples, you test all of them. Because with auto samplers and so on, running 20 runs is not a problem. Okay, but if you get over 20, then test 10% of the remaining ones. So if we had 100 samples, we would test, say, the first 20 and then 10% of whatever's left. So if we have 100 bags, we're going to start with 20 of them picked at random. Then we have 80 left over. So what's 10% of 80? 8. So we would pick 28 bags out of 100. And that would be a really good rule of thumb. It's not, it's better than just 10%, because 10% would only be 10 bags out of the 100. This is testing 28. That's a lot, but it's not a huge burden. You're not testing all 100. After you've tested 28 of those, you're going to get a good idea of the variability in those 100. But you need to test them randomly. If you're looking at 100 and half of them are blue and the other half are in green bags, you've really got two different groupings. So you don't have 100, you have 50 and 50. Okay. So then you would test 20, and then you would have 30 left over. So you'd have 23 out of the first group and then 23 out of the second group. So you would have 46 tests. Okay, but still, that's a better way to go. And then you would want to see if there's any statistically significant difference between the green-blue bags and the blue bags. Okay, and we'll get into that a little bit later. We have 3 different seizures, seizure A, B, and C, and we'll look at how to analyze that data. Okay. So that's all I have for today. This right here, though, even though it was at the end, is probably the best equation in this whole set of notes, because this is money right here. How many runs you do, and so this is a good rule of thumb. But whatever lab you go into, they're already going to have a procedure for how to choose the number of data points that you want.